Okay, it's working. Hmm. Hi, Keshav, Sujay, Rutvik, Anik. How are you guys doing? Can you hear me?
Yes, yes, we can hear you. Hi.
Hi,
Yeah, it sounds all good.
great. Today it's gonna be very exciting session because I'll share my screen. Hmm. Okay. Can you see my PowerPoint screen? I hope. Yep. All right. So in today's session, we will cover up a few of the algorithms, few of the deep learning models we discussed last time. First, understand the theory of graph neural network. Then we'll do one hands-on Colab implementation. And, we'll discuss one graph neural network application, structural engineering, that which is a paper published by Autodesk recently. And later we'll have time for brainstorming and discussion for ideas. Uh, I would request for all the Zoom attendees if you can mute your mic. So, and later during the discussion, or you can
কেউ
also
খোলো আমি খাচ্ছি
Anik. Okay, maybe I'll. Awesome. Thank you. So, quick recap of deep learning models. So, I have this article. One thing which I would like to I like to focus on is you will find a lot of relevance of convolutional neural network and autoencoder once we get deeper into graph neural network. So keep an eye on those models, how their architecture is, and then we will able to correlate some functionality between these models. So I'll start with basic MLP, where you have sets of variables in input layer, and then you create the model architecture with a lot of deep layers, like a lot of hidden layers, and that's why once you assemble a lot of layers, it's called deep. And depending on the problem you're trying to solve, whether it's classification, regression, you'll have an output layer accordingly. So one problem is classification of cats or dogs. Another is if you have multiple classes, like 10 different types of flowers, then you will have accordingly 10 nodes in the output layer. So this is a basic uh, multi-layer perceptron model. Second thing which would be quite useful would be convolutional neural network. So basically, uh, imagine this. So down one disadvantage of MLP is it has every information in this a linear pattern. So in order to have another model work in MLP, we need to flatten it so it's a one directional vector. But since if you convert an image into one directional vector, let's say flatten it out, it loses a lot of important information, which is its which is which it can extract from neighboring pixels. So for example, if I have this 28 by 28 pixel image, which is, and I flatten it into one dimensional vector of 784 nodes, there are important information which are like say adjacent pixel value, that this edge is related to another pixel or it's continued to another pixel. So that continuity is lost once we flatten it. So that's why this convolutional neural network is quite successful in terms of identifying lines, shapes, edges through this type of architecture, because it maintains the integrity between neighboring pixels throughout as we go deeper into the network. And so, long story short, initially the model, uh, you have filters which identify edges. So if it's a face, you will identify the horizontal and vertical edges in the face. Then in the later layers of the network, it will be able to find correlations between those edges and try to figure out overall shape or object. So if let's say if there are two horizontal lines and one vertical line, the network can form correlations that okay, it's eye and nose which is extracted from this network. So hence initial layers are very basic edge detection and later layers are overall shape detection in CNN. And yeah, same, you can do like a prediction of whether a person is wearing a safety helmet in this image or not. So different type of problems you can solve for object detection, various computer vision problems through CNN. And lastly, which and at a very high level, you can also say that this 2D 2D matrix is kind of a graph where each each node, each pixel are connected to adjacent to each other. So there is a rising research, and graph neural network has become a hot topic these days because a lot of problems can be translated in the graph neural network through graphs, which, for example, transportation of, like, there are various location and how your bus is connected to those locations, that can be easily translated in a graph network compared to solving that problem through either an image based model through CNN. So that's why, like, a lot of time machine learning problem, you start with what's the major idea you have, what are the various architecture model you can use, and how can you abstract your main problem into features and then features into final prediction. Lastly, uh, the last model I want to discuss is autoencoder. So basically, let's say this is a 28 by 28 pixel, and in this first layer there are, because you flatten it out, there are 784 nodes which will be created. And then you, in those progressive hidden layers, you reduce the amount of nodes to abstract the original content of the image. So let's say from 784 in first layer, it can be converted into 10 nodes. And this middle part is called bottleneck, where it's all the input nodes are converted into a latent dimension where uh, the information can be extracted. And then later, this bottleneck is converted into again original image of same nodes, and this is the output. So you might think, okay, what's the use? You are just giving an input image and also extracting the same output image. But it, the main utilization of this kind of generative model comes when you remove the first part, the encoder, and just use the decoder part, because now it's acting as a generator. And you might have seen like latent space walk videos where there is a morphing of between different numbers 1 to 3 or 3 to 4. It's because in this latent space, you have, now you can play with different variables, and once you tweak those variables, it generates different images based on just numeric values. And also, it's useful when you are transferring files, when you need to compress a large file, and then in the final location you can decompress it using the decoder network. So this is very high level functioning of MLP, CNN, and autoencoder. Now, what is graph network? So basically, it comes from mathematics, where it's a representation of nodes and nodes which are also called vertices, and edges. So as you can see, this circles are nodes, and the connection between them determines the edges. There are two main types of graph: directed graph and undirected graph. So directed graph has, like as the word says, some direction. So it's not both ways; it's one way. Like uh, imagine there is a only one way route from location A to B, but there might be few routes which are two ways. So depending on the type of data you have, you will end up having a directed or undirected graph. And I have example. Yeah. So basically, yeah, this is the way directed graph where there is one direction between all the nodes, and in undirected it's both ways, so you don't need to. And a good example would be like if you become friends with someone on Facebook, it's both ways, so you don't need directionality in that. But if you follow someone on Twitter, it's one way because that opposite person might not follow you back. But so as you can see in this, it's a directional graph. So to conclude, V are vertices, which also called nodes, and E are edges. And you label it for all the nodes. So with this set, and you also define all the edges V1, V2, V2, V1, V5, and you make this set. And overall, the graph is this G equal to V comma E. So hence all the information is defined in this set. Okay, yeah, and just to ensure we are clear, directional graph, when you define edges, it it contains the directionality. So it's V1, V2, not V2, V1, because if you define V2, V1, it defines the opposite direction. So cool. So you might wonder why graph neural network, like what's the neural network part in this and where's the deep learning happening. So we just discussed nodes and edges, but uh, for example, we will look into this problem later, where you have a building, and building has columns and beams, and each beam have different properties such as cross section area, reinforcement, material. So those properties, let's call it features. So if each beam is a node, let's say V1 or V2, so each node has its own set of properties. It can be a list of properties which define the structural behavior. And let's say at the end, you want to create a neural network or a machine learning model which predicts whether this beam will fail or pass, or if you want to do optimization. So now all the features, let's say if you have identified 15 features which are properties of beam, ultimately that network you will converge into an output layer, which is whether the beam is pass or fail. So we are converting that. Let me annotate. Hmm. So basically, each each node has sets of feature like area, material, and you will train this network to output one node. So if I just abstract this node, there will be sets of features, and then we can have similar embedding, or in either you can also make a MLP model where you can have hidden layers, and then you can output whether it fails or pass, or like, yeah. So you'll form a different similar neural network within this. So this is, if you just treat this individually, it's a similar MLP network where there is a set of input nodes and output. But the main advantage of this network comes when you you find correlation and aggregate information from other nodes. So let's say in a building, the change in size of this column will affect the loads on this column, like dead loads or any other parameter. So that's why when you do multiple steps into the network, you will start aggregating information from other nodes. So you, I think it would be more clear once I have a next slide where how different information from different nodes is aggregated in an individual node. And when you go deeper, this node, let's say one particular node, will have the information of all the nodes because it's averaging over each node. So for example, in the first average, this node has information of this node and this node. But in the second round, because this node is also getting average, it has information of the nodes it's connected. So in the next time step, when you do average, also information of this node is transferred, but this has information of this node. So all the nodes contextuality and information is transformed into one single node. And yeah, so I have let me check if I have enabled sound, because this video will explain quite better. In an individual node, and when you go deeper, this node,
In a second, how
let me
exactly
know
this
if you
works.
don't hear.
First, let's have a
sound.
look at this visualization from a paper which shows image convolutions on the left and graph convolutions on the right. For images, you simply slide learnable kernels over the regular
Can
grid
you comment
structure
if
of the
you can't
pixel,
hear
which
the
extracts the
sound?
most important information. This can also be seen as combining the information in a local area by using all the pixels in this neighborhood. For non-Euclidean graph structures, this idea is extended, as we simply use the information in a node's neighborhood and combine it into a new embedding vector. If we look at the red node in the graph, this simply means that the neighboring nodes share their current embeddings with it. This is done simultaneously for all nodes. This sharing mechanism is also called message passing, as the states can be seen as many messages passing back and forth between the
For some
nodes.
reason, I can't
But now let's
access
have a
the
look
chat.
at a concrete example to better understand this idea. Let's assume
So,
this is
yeah,
our input graph
each
in the
node
following.
decide the
We
different
see that there's one
features,
yellow node with the number 1, with a
and
yellow node
just
feature
keep
vector
a
or
track
state.
how
This is the
different
node we will
colors
focus on in the following.
which
To update the
represent
node state,
different
we
features
collect
from
the information of the
this
direct
nodes will
neighbors,
be
which means
aggregated
we perform the message passing.
on one.
What we end up with
This
is
is
the
called
information about our
message
current node state
passing,
and the information about
which
our
makes
neighbor's node states. These
graph
states are
neural
usually
network
denoted with
unique.
H. Currently, we are in time step K. Then we perform an aggregation on the neighbor states to combine their information. Finally, we put our current state and the combined neighbor information together to get a new state or embedding in layer K+1. Note how some of the feature information of the blue nodes enters the state of the yellow node. Now we update our annotations in the graph. This message passing is done by all nodes, and therefore we have new embeddings for every node in our graph. The size of these new embeddings is a hyperparameter and depends on the graph data you use. As you can see, the node with the number
You
5
can also see
only
that
holds information about
the
the blue node
features
and itself, because it's green and blue. Currently,
increase
this
from
node doesn't
50
know
to
about our yellow
128.
node with the number 1. But this will change. Let's perform another message passing step to see what happens. And actually, we can perform several of these message passing steps, which corresponds to the number of layers in the GNN. Again, we use the current node embedding of our yellow node, collect the state messages of its neighbors, and aggregate them in some way. If we update the yellow node's embedding now, we can see that some information about the green node passed into it. This means that node 1 knows something about node 5. But additionally, in our example, every single node in the graph knows something about all other nodes. This knowledge is stored in each of our node embeddings and contains the feature-based as well as structural information about the nodes. Eventually, we can use the embeddings to perform predictions as they contain all the information about the graph that we need. And this is the basic idea of GNNs. We learn these embeddings by iteratively combining the node information in a local neighborhood. Iteratively means we first learn something about the direct neighbors, then about the neighbor's neighbors, and so on. This local feature aggregation can be compared to learnable CNN kernels. We can actually visualize how deep we dive into the graph from each node's perspective. This means we can understand which neighbors and neighbors and so on we learn about. This is usually called the computation graph for a specific node. If we restructure our graph like this, we can automatically see which nodes are the direct neighbors of our yellow node. This means in the first layer of our message passing GNN, the yellow node incorporates information about the blue nodes. Now if we add the direct neighbors for each of these nodes, we can see the next layer. 2 of our blue nodes are connected to blue and yellow, and the third blue node is connected to green. We can see that after 2 layers, the yellow node already contains the information about all nodes in the graph. The number of layers in a GNN defines how many neighborhood hops we perform. This number is a hyperparameter and depends on the graph data we use. If you have small graphs, such as smaller molecules, you can quickly learn all the information after only a few layers. The number of layers also depends on the learning task. Sometimes only a local area of the graph might be relevant for your predictions. But stacking too many message passing layers in a GNN can also lead to a phenomenon called oversmoothing. As you see in our previous
Okay. So now, before moving ahead, I would just like to know if you have any questions or clarification. Because if we know like basic functioning of GNN, then when we start implementing it in Colab, you'll be able to like relate more. So I just want to know if everyone is clear. If anyone has doubt, we can do like a couple of minutes discussion. Feel free to unmute your mic.
Hi, Mayur. I had a question.
Mhm.
Yeah. So the first thing that I want to understand is the number of layers in a GNN is equal to the longest chain that you might have in a graph.
So one thing to consider is the number of layers here is each node has their own neural network. So it's not all the nodes are equivalent to the input nodes in MLP. So each node, let's say we have a neural network of 5 time step. So in the first time step, this node will get average information from the 3 nodes it's connected. In the second time step, again, it will do the same aggregation of information from these 3 nodes. So if we have 5 time steps in our neural network, there are like 5 times it will aggregate the information. And before the aggregation is done, that is where the neural network comes into play, where it will decide how much weight it will give to different nodes. So for example, this node has 3 connection. So it might, the neural network will decide if we need to give equal weight to everyone or more weight to this node compared to this. So each node has their own neural network, which depends on how many time steps we need to do aggregation. Did I answer your question right? That how the neural
Yeah,
network?
I got that.
I can even.
Also,
Sorry, go ahead.
the other question that I want to ask is each time step you're doing one kind of operation onto that. So
Correct.
can you in each step do a different kind of an operation in terms of aggregating the information? Like you can when you assign the separate weightages for each time step.
Yeah, so that comes how you define the model in the time step. So for example, few models have mean or max pooling, so where they will apply those nodes. But so I need to check whether I have the equation. But your question is, can we define the weights for each layer, right? Or
Each time step rather.
each time step?
Each time step which might aggregate towards a greater towards an end towards the maximum or minimum, that as one way to put it is something like that.
Correct. So we don't want to hard code the weight, because that we want the neural network to learn the weights for different aggregation. Because let's say you have uh, a structural model of column and beams and column of few stories. So there might be a weight where the beam influences the column more compared to the column above. So we want to give the freedom to network to learn the weight when it's aggravating,
Okay.
because we don't know like how much each node will affect the existing node which we are aggravating.
Okay. Okay, fair enough. Got it.
Yeah, those are good questions. Yeah. Let me check if yeah. So this image, you can see each node has its own features, and this one block is our time step. So for example, this network has 4 time steps to do the neural network training. So basically I think there was a good discussion in this video of 2 hours. Let me check if I can quickly show the image.
Hello everyone. In this lecture, what we will discuss
Hmm.
mathematics using G vectors. Neighbors of C are
Okay, yeah.
A,
So this
B,
is a
E,
really
and
good
F.
image to
That is, C is
understand.
connected to most of the neighbors,
So
and
A
neighbors of
is
D
our,
are
let's
A.
say, input node
So in
with
this way,
X
what we are doing,
features,
we are forming a
where
two-layer.
X can be 1 to 10. And we are defining what are the nodes here which are affecting A, B, C. And this gray box is our neural network. So all the features which are coming from these nodes, and before aggregation, they pass through a neural network, and then they are combined with original features of B.
Mayur, this example actually is quite interesting, because this is something that what I was trying to ask. Like for example, if you look at the network that is formed where A is influencing D in the this thing, that is only one time step, and it only that D gets only information from that A node, whereas the C and B runs multiple time step to aggregate more information. So, which is why I was asking whether do we need to adjust weights, because because in couple of nodes you're getting more information which is aggregating over time, as opposed to one node which is just being getting information from one node and
Got
over the same amount, over one step or one generation, I would say.
Yeah, so that's a good point. So
So
this
the
is
thing is that
just
if there
for
are, would it create outliers, or would it create some sort of extreme conditions in the final? This thing is.
yeah. So I just want to clarify. So this is just we are monitoring node A, and this has like time step 0 and time step
Yeah.
1. But the network will have parallel training where there will be a node B which has a relation of let's say this is the neural network where this is A and C. Then again there would be neural network here, and we'll see connection. So every node there's a parallel computation going on. So there's no like, even if the node has less connections, it doesn't imply that it's learning faster or slower, it's has less weightage. So imagine, like for example, if node D is a start of an airport location, and all the bus routes start from that to all the locations in the city. So because A has no connections previous, it doesn't imply that's not an important location. So that's why the network will learn different weights, that when A is connected to B, C, and D, it might come out that D has more weight compared to this two. That's the learning the network does.
Okay, yeah, got it. Thank you.
Yeah, no problem. Thanks for asking. Cool. So it's 30 minutes, and I will jump into The next part. So we know how so basically very high level is uh, we want the influence of other nodes in the node we are monitoring. So that's why doing some average function or max function of features from other nodes and adding it to current node, we are developing how the changes in other node will affect the current node's values or features. So that is one relation which we are training in this network. Cool. So I'll just quickly go through some of the applications here. So uh, it's it's taking it's being useful in physical systems where various laws of physics, which sometimes are very computationally heavy or it's non-differentiable, you can convert into differentiable parameters and do training and do faster computation. So similar example in AEC would be doing structural analysis of a building where all the members are connected and it follows laws of physics. And that in the paper we'll discuss how Autodesk has created a network where they train for that problem. And yeah, also in physics, like this chemistry problem where you can define like each atom as one node and the edges as connection, and maybe each node, let's say O, will have the feature information of what kind of bonds it has with another atom. So those features carries some information in image classification tags. Yeah. One, I think we'll briefly discuss this. So a while ago, I trained a StyleGAN model to do generative floor plan. The problem with that was it was able to create different floor plans, but there was no explicit definition of various rooms or constraints on those rooms where, oh, I want a corridor between these two rooms. That thing I was not able to define explicitly. But this is an example of using graph plus GAN, where we are using the advantage of graph neural network to define relation between different rooms, and you can see different floor plan are generated which are more realistic compared to just a GAN model or just a style GAN model. So we are done with that. Yeah, another way then these models are useful is what you can do is, let's say you have a network and you want to decide it's very it's let's say in Bangalore there's a very busy traffic, and then you want to start a new bus route and you want to identify what would be ideal bus stop or a location where we can reduce the traffic as much as we can. So you can define a node with with either null features, and once you define, like let's say you identify 3 to 4 locations and you want to know what's the best location, then the network will be able to predict what node would be ideal for that. Or if you know already a location that I have a bus stop, but we don't know how much frequency the routes should go, then you can do an edge prediction where the edge can also determine the frequency. So either you predict node or you predict edges, or you do overall graph classification where you can say, let's say a molecule falls into this category or not, because the whole molecule representation is done in form of graph. And now it's time that we do implementation, and I will share this link in the chat. So let me know if you face any difficulty in accessing it. I will also share on the live session. Cool. So I hope it works for everyone. Give me 1 second. I just saw that my battery laptop is running out of battery. Sorry for this. Okay. I hope everyone is ready with the collab. If you want to save the file locally, you can do a save a copy in Drive. And first thing, I think, change the runtime to GPU if it's not there. And I will first let you know what the problem we are trying to solve. So we have different molecules information, where there are atoms and combination of that is encoded in string format. And for the molecule, we are mixing it with water, which is a solvent. And we want to predict how this, what's the proper word, the solubility of that molecule. So that's what we are training. And like, I think the like uh, rule based approach would be like you have a molecular formula, you do different chemistry equations and then try to predict whether you can solve it or not. In this network, we are not giving any information to them, just from the basic data from training, where we are giving different molecular structure and its solubility properties. It then learns that what are various atoms and what type of bonds uh, tend to have more soluble character. And when we give an input of new molecule, it will predict the output of that solvent solubility. So this, like, initially I was not very sure like how we can decode all the complex laws of physics into a network. But once you start training and like experimenting with different models, you'll start realize the potential of how like different complex phenomena can be decoded just from data. So this uses PyTorch, and so we are just installing the graph neural network library. And okay, I might have run all activity run all command. So you just click on this and you will able to see. So this works on CUDA. So that's why we are just checking whether we can access that. Then we are installing the library PyTorch. And so this block, the network, generally in order to install a new library, we use pip install the name of the library. But this specific RDKit is not available through that medium. So we are installing using Miniconda. So this is the code for that. So it's basically prepping all the required uh, environment to run this code. So it's still running. This sign means it's still running. And you might think, what's the need of these libraries? So when like all these libraries have inbuilt functions which you can extract to do model definition and training instead of defining all the function from scratch. So that's why even in reinforcement learning or GNN, it's important that you identify what are the available libraries which you can use to define a model, or even a lot, like for example PyTorch geometric have gives us access to dataset also. So we will see soon how we are accessing the dataset function. Yeah, so you can see it's installed. It has installed RDKit. Let's see information of the dataset. So as I said earlier, our model has all the molecular structure information which are solute, and we want to predict how it's dissolving in water. So the dataset has 1128 compounds, and this is a figure of that compound where you define like this network and the edge connections. So one thing to note is for our current dataset, we are using existing features. So I will show you. From let me check if I missed out something. Is anyone else facing this same error? I just ran before it was, so it says define simple.
Yeah, checking. I guess it is related to either PyTorch has not come properly installed, I guess. Can you please run the previous one again?
Thanks. So it ran in your collab correctly. Okay. Why is it undefined symbol? Mm-mm. No running to the CUDA is animal. Undefined torch. But here it's showing that the torch is installed properly. RDKit is installed. Not good. Is anyone else able to figure it out, or?
Yeah, no issue. Can you just show me the OS error? Let me check from the Google also. In the meanwhile, it is kind of.
Yeah, okay.
Uh,
Time to decode this.
I think undefined symbol. I work probably install the same version. It might be some version.
Let's see. Oof, not expected. People, okay. I think it's mostly the version issue. Yeah, let's see if this works. Otherwise, I'll just run you guys through the
Yeah,
code.
no issue. I think there is also kind of conflict between the counter level packages and peep packages. So it gently happens. So no issues there.
So, so how do we resolve that?
Basically, I did on conda level. So
Is it working in your collab? Oh, like
let me
instead of
check.
pip. Okay.
Yeah.
It's taking a while to install. So if it's running this gray symbol, once it's finished, it will turn into orange. So let's see what we can find from other articles. Okay, you must restart. I want to check first. I need to do again. So it's already 1.6. Let's give one final try. I think the intent was for the collab part was to go through how the network is constructed, and if you want to implement similar model, what would be the approach. So if this doesn't work, the good part is we already have the sample output for each of the codes, so we can just discuss that. All right, I think let's just move on because it's already 50 minutes has passed. So, okay, uh, this first four lines are giving information about the data set, and we are extracting that data set with this part. So the good part is like either you can make your own data set or import from other areas, but Python Geometric has their own data set which you can directly extract like this. So once you have the data set, you need to, if you might need to do some, uh, get some insights. So each node has one feature, and this is the output node, which is giving one value. It's giving value. So you can see there are total 32 nodes, each node with 9 feature, and that has an output node of 1. There are total 68 edges. Yeah. So we got some insight about the data set we have, and just to get a feel of what how those features looks like. So this is the array of each node, each 32 nodes, and these are the 9 features per node. Yeah, so x1 to x9, total 32 nodes. And so once you either go deeper or look at the videos I shared, so one way to work in this model is to prepare adjacency matrix, or you can also make tuples. The good part is it saves a lot of memory, where the adjacency matrix, depending on the nodes, so we have 32 nodes, so it would be 32 by 32 matrix. So this is how you're saving some uh, memory. And so it has one output node, so it's normalized, and you can see it's between -1 to 1, the value of a particular graph. All right, so this whole molecule data is, you can decode it using, like, Smile is basically getting it into a string format. So this is how this molecule is defined. And we are data 0 means we are just viewing the first graph of the whole data set. So, okay. And you can also see the information of the molecule. So if you want to know more information about the data set, you can always visit the PyTorch Geometric web page, where they will have different uh, variables through which you can get different insight about the data. So there would be like a type variable which gives this output. So you can look into that web page. So this is now the main part comes of implementing it. So this is a class definition, and we discuss about different time steps and embedding. So we saw an example earlier where in that video there were 50 features, and in the embedding space, the first time step, it was converted into 128 features. So for our network, we have 9 features, and in the first embedding, we are converting 9 features into 64 features, and we are running it in four time steps. And in the output layer, it's a linear layer, and we are predicting uh, whether how much what's the solubility. One thing is important is we are doubling the embedding size. So what we are doing is, when we are for this final layer, we are doing a mean mean of all the nodes. So that would be a 64 uh, dimensional vector, and we are taking max of all the nodes, and we are appending it. So that's why from 64 we are into space of 128, and that molecule will be predicted. So I think a sketch would make it more clearer. Just give me a second. So for example, there are 32 nodes connected differently. Each node has the 9 features which we want to train. And if I represent this as vertically, these 9 features are first projected into the embedding space of 128, and then we are doing 4 time steps where in those areas we are taking mean and aggregating the information from adjacent nodes for 4 time steps. So by the end of this time step final, this node in this embedding space will have information of all the remote nodes, because while aggregating all the information has been transformed. So once we have this, we are doing mean of all the adjacent nodes, we are doing max of all the adjacent nodes, and from 68 we are converting into 128. Oh man, I'm running out of space. And then we are just doing an output prediction between -1 to 1. So there would be a final output layer here. So this is how this network works. And yeah, so these are the hidden layers, and this is how information is moving in the forward direction. And yeah, so remember we talked about pooling from 64 into 128. So this is doing like mean, max, and then appending it. This is our output layer, and this is how you define the whole network. And you can see the 4 layers, the output layer, and the dimension from 9 features to 64 features in embedding space, 4 time steps. Yeah, and then pooling. So once we define the model, the next step would be training it. So as typical deep learning model, you define loss function, optimizer, and then you run the training, and also like basic definition of batching the data set. And I think if you want to uh, have a bit deeper understanding of this, there's another video which is like the third video in this series, where he also explains how the batching works in some through a graphic, because this is not like a typical batching for images where we have all the images in the same dimension, because different graph have different different nodes. So there can be one molecule of 32 nodes, another molecule of 36. So how the batching works is also an important fact to know. So yeah, we are defining optimizer, loss, and that's how we are training the network. And as we saw in, I think, this video, through that loss, it's getting value for the updated weight in this neural network, and that's how our model will be trained. So once we train it, we can visualize the loss. As you can see, it's decreasing with time, and we ran for 2000 epoch, and you can see it's very minor loss. It started from this. So once it's trained, you can see the actual value versus the prediction of this model, and it's very less. But for some molecule, it's a bit different. But we ran for very less epoch, and you can see y prediction versus y real. Ideally, it should be a straight line because both values should be the same. But there are few molecules which have larger loss. And I forgot to mention that while defining the data set, we are differentiating how many molecules go to training and testing. Where is that? So we define the data set. Data. I think there's one code where they are saying in test data equal to 0.2 and train data equal to 0.8. So it means 80% of the input sample are used for training. Oh, yeah, I see. It's here. So the data loader function does that. I hope it's clear how the model works, what it's trying to solve, how is it predicting, how the training works. Any questions? Cool. I think the crucial part now comes related to AEC application, which I think will open up some insights about how you can apply this model in your day-to-day work. Cool. So this is a very recent paper by Autodesk in which they are making a model where there is a neural sizer, which is a graph network. So based on the skeleton is basically all the column and beams you define in your structure. Neural sizer will do the initial sizing for column and beams, and then neural sim will do simulation where it will compute what's the drift ratio for each story. And so there's a codal provision that uh, for structure the drift limit is this value. So then it will check whether the current drift is higher or lesser than the drift value. If it's higher, it will penalize the network and it will do the training so that the next time it's sizing, it will size, let's say if it's failing, it will size a bit heavier section so the drift limit is within control. So this is very high level overview about how these two networks are trained. Yeah, neural sizer is for assignment, neural sim is for evaluation. Is there important structures create end-to-end pipeline? Yeah, and just to give a context, so this when you are dealing with big structural models, it takes a long time to do optimization and computation. So that's why few people tend to adopt a approach of starting with thumb rules and do few calculations. I tried one way in which I was using Karamba and using Galapagos or to do the genetic algorithm based optimization, but it was taking a long time for each iteration. So that's why when you are short of time or you want to do a optimum sized approach right for your initial schematic stage, this kind of model will help you to save a lot of time as well as have a good sizing without any uh, biasness of thumb rules or other implications. So yeah, so this it discusses typical models and uh, challenges, and there's a brief discussion that you can also combine different models. So as we saw in this paper, it was combining graph with GAN. There's also a model where you can combine graph with reinforcement learning to train the network. And there was a model where it was training a tower to not fall and how to stabilize that tower. Cool. Variational autoencoder. Yeah, then it discusses GNN, VI. So we talked about autoencoder, which is a VA is basically variational autoencoder where while defining the model and in that bottleneck, there's you add another function which allows you to manipulate parameters. So let's say I'll draw. Let so let's say you have a network and this is your embedding space and you have a face. So based on this input vector, it generates images of a face. But then if this is so one set of input produce one set of image. But if you have VA, if let's say it's a 10 dimensional vector, then if you manipulate these values, it can generate different faces. So basically VA tries to uh, allows us to manipulate this bottleneck vector where we change different values of this and we can create different images. And I don't want to go deep into it, so then it's entangled basically, so keep that in mind. So if I let's say if I just change this value of this first dimension, it's not necessary that it will just change uh, lips from serious to smile or hair from short to tall. Changing one value will affect multiple features. So it will tweak some skin color, hair growth, smile. So that's why in order to have an explicit representation that I want an I want an embedding space where each sorry want an embedding space where each dimension corresponds to each feature in the image. So let's say first is growth of hair, second dimension is smile, something. Then you need to do disentangling, where you basically do another sets of operations on this space, and you can disentangle in one. Then you have similar dimensional embedding space where one dimension corresponds to one feature. So sorry to overload you with a lot of information, but just keep in mind what is VAE, what is disentanglement, this entangled space. So when you see different models of StyleGAN, you know that you might have seen a StyleGAN model where there is a slider and you move one slider and it will change one feature. So that's not VA, that's disentangled space. Okay, why am I not able to erase? Okay, 1 second. All right, so let's move to the next. So we know the importance of this graph neural network and uh, what are the advantages. So this type of network helps when you have a large network or a computational space and you want to do fast computation with your neural network, because the network has already learned all the weights. So imagine this. So if you are doing a structural optimization and you change different column sizes of each story, with each change it will affect a lot of loads and sizing of other columns. So it's a non-linear space where one change will affect a lot of other parameters. But if you do approximate that and do a differential uh, model using neural network, you already have computed all the weights. So you are just inputting one input vector and it's doing all the matrix calculation to do one output. So that's why that is one of the reason I believe uh, this model does structural optimization faster than conventional genetic algorithm based approach. Yeah, so this defines what are the loads they have considered. We are basically using this approach of making it differential. And it's also like, as we saw in graph neural network application, there was first section about physics. So it's this area. So basically we want to minimize the total mass. We want to ensure that the drift ratio are in control. And we also want that there are limited structural section, because you can make a building optimum for structural mass, but there are so many different type of structural sections that it will increase the transportation, the different types of connection costs. So that's why they have limited to, I think there are like 6 or 9 sections for beam and 4 sections for column. So these are the constraints we have, and they are doing random data set generation. And for training, they are computing the values from this network and with the robot structural analysis simulation. So this is a representation of this building into graph, where the orange columns are represent as this node and green as this node. Okay, so how this works? So it has encoder, propagation, and decoder model, and I will talk about it. I think I have something which might make it easier. So they have defined the network in detail at the later part of the paper. So these are the sections from which it's choosing. So we talked about nodes, edges. In each node having feature. So in the collab model, there were 9 features per node. In this model, yeah, in this model there are 19 features per node. Okay, so each node has 19 features, and it can be section size, material, where it's located, connectivity, start and end point of that beam, various elements. Then, as we saw earlier, once you have that input feature space, you enlarge it into embedding space. So in that example, it was 9 to 64. In this example, it's 19 to 512. So once you have enlarged all the vectors, feature vector from 19 to 512, I think I'll also draw it. So, so, mm, so you have 9 feature vector. You have enlarged it to 512. Now you got the embedding space. Now, as we recall that once you have that, you start uh, aggregating features from adjacent node. So with each time step, you do average of nodes surrounding it, and then you embed that information. So in this model, they have done for 5 time steps. So what they're doing for each time step is, there's a function SLP message which takes mean of all the adjacent nodes. So VI is the node we are inspecting, and VJ is all the nodes that are connected. Then we are doing this position aware message, which is I think let's uh, leave it for a moment. So basically, we are using aggregating the neighboring nodes using the position aware, where it gives more weights, if I'm right, to the nodes nearby, and the amount of weight and exploration decreases with each time step. And after that, you do this aggregation, update node embedding, which is the step equation 4. So for each time step, you do this 3 computation. And then what we are interested later is, um, once we computed, so there would be 5 time steps. Once we computed that, now we do average pooling for all the nodes per story. So there would be, like in the Colab example, a similar area where we do like max or mean. So they have their own function where they do average pooling per story. So now this is data per story. And basically they have a sequence how they do it. So they start from roof to the floor below. They do story calculation for that, average pooling for that, and then they do again for the floor below to second last floor. Because like based on structures, it's when you calculate drift, it's you subtract it from the roof to second last and then second last to uh, yeah, it's the way how drift is calculated. So this is a recursive phenomena, and they just labeled it as structured decoder for these two time steps. So this does the average pooling for our network. And once we do that, and we do that recursively, so now this goes to MLP network, where we are just using these nodes to create one prediction where it will say whether it has crossed the drift limit or not for each story, and it will also calculate the drift value for that story. So as you can see, the HK is the prediction of exact value, and CK is a classifier whether it's within limit or not. So this whole network is neural sim, where we are just making a network to do prediction for drift and classify whether it's code compliant or not. So this works when we get the dimension. So this already has the dimension data, and where it's getting the dimensional data from neural sizer, which is this one. Let me clear. So basically in neural sizer, we are not, sorry, does not compute position aware message by virtue. Yeah, so basically for this is called propagation step, where for each time step it's propagating in the network, and the dimensional change from 19 to 512, it's called encoding step. So, and the last step we did for classification from each story to whether it's falls within a code limit or what's the exact drift value, that's the third step called decoder. So remember we saw earlier that the neural sim has encoder, propagation, and decoder. So this is how it's breakdown in the computation. Yeah, so neural sizer basically it has similar. So in neural sizer, instead of 19 uh, values in feature space for each node, we are reducing to 10 and do not contain cross section, because that's what we want to predict through this network. So yeah, and for the propagation part, we don't do the mean position of our message. And rest, the network is same, where here we are doing, sorry, for same we are doing average pooling per story to calculate the drift. Here we are doing average pooling for all the nodes, not just nodes on that story. And once we do that pooling, we do this softmax function, which will predict what's the section size. So my guess is, for if the softmax function, like the output has a vector of, let's say, 10 values, it will predict from the one hot encoding. Let's say the first vector would be this beam, second vector would be this beam. So it will be able to say from the softmax where this is 1 0 0 0, So for that node, this is the beam size. Okay. I think, yeah, so we understood the model architecture for neural sim and neural sizer. And just to conclude how it calculates loss. So yeah, so loss is pretty straightforward, where you calculate the difference in drift computed by OK, like for each story in the neural sim, versus the results you get from robot structural analysis. And for sizer, yeah, so you define total mass, drift constraint, and variety constraint, and entropy. And this is the total loss function for sizer. So you have loss, you have model architecture, you do training for the batch, 5 bucks, 50,000 epoch for training. And yeah, and then later it just says that how the results are better than genetic algorithm, how it's faster, and also like different way would be one can also utilize this as the starting point for genetic algorithm, where you can get the sizing from neural sizer instead of doing a random size input to your genetic algorithm. Because if you have a more realistic sizing input, the convergence for GA would be faster. And also if you want like initial design, quick feedback, and quick sizing, this is a good network. Few of the limitations are skeleton can be included into, yeah. So there are two different graphs for sizing and simulation. It says the skeleton can also be a part of this graph network. Maybe they have done it separately to simplify. And second is this just covers column and beams, so no structural walls and flow panels. Yeah, and also the drift limit is kept constant. So different codes have different drift limits, so you might need to change the drift limit accordingly. Okay, I think that's it for the AC applications. And we are already 1.5 hour, but I think next time or in future it would be good, or it would be interesting to discuss this house can where we can, okay, I will explain very high level. So basically you have this graph node and you do operation to generate the room mask, and you compare it with the real floor plan data set you have, and you do the same algorithm to create the room mask from the data set. And basically the discriminator will try to predict whether it's real or fake. So it will generate different room mask, compare it with the real room mask, and whether it's fake, it will change the training and the probability distribution in the discriminator network. And there will be a renderer which will, once the network learns to create more realistic room mask just from the input diagram, this network will be able to create different floor plan layout. Yeah, I think the good part is I did a collab implementation of for this, and we can maybe discuss in future how to implement this network, because they have shared the basic code for the whole model in GitHub, but they haven't shared for the structural model. So it's again by Autodesk. So a lot of stuff we discussed. So yeah, now it's time for Q&A. What do you think? If you want to clarify any stuff, any comments about the structure of the session?
Hi, Mayur. Just wanted to understand one thing. So GN input would give a more emphasis on the hierarchy of classification as compared to the other networks, right? So you can define a skeletal structure of hierarchy, and then that would be improve the training if you want to. So how so and you give an example about how reinforcement learning can be combined with this. Wouldn't that be kind of conflicting? You have right. I was trying to imagine how that works.
Sorry, I couldn't get your last point. Uh, you said how reinforcement learning can benefit.
So
Yeah,
also, so you have one line of training where you're trying to train the GNN network,
correct.
which is this thing, and on the other line you have the reinforcement learning algorithm, which is also directing training. So I wanted to try to understand uh, when you're trying to combine both the training, because I'm not able to visualize how that works,
Oh, I see.
because there is one hierarchic structure which is being directed by the GNN, and then there is another hierarchy that has been given by the reinforcement learning.
Got it.
So I'm just wondering, would there be a conflict? How would that work, or is there some kind of aggregation that happens?
Yeah, so basically, what I understand is that a reinforcement learning algorithm will affect how the loss and training is done. So the whole
Okay.
network would be as it is, but instead of loss, we'll have a different reward structure where the weights will be able to learn differently. Or you can also add few other. It depends on how you integrate the model. So like in this, i i I think they're using discriminator part of GAN for the training purpose, but they are using the input model from GNN for the generation purpose. So it's not generative apart from GAN. They have taken generative part from GNN. So it's basically how you compute loss. Like I can also compute loss from GNN, but I think they chose to train the model using loss from GAN. So
Okay, thank you. I
yeah,
think I'll have to look at that more in a more slightly more detail, because yeah.
yeah, I think yeah, it's I also need to study that in detail, but I just have like higher level understanding how it might be combined. Maybe yeah, if I find something, I'll share it with you.
Sure, thanks.
Cool. So so I think it's important that we understand what are where is that article? What are the applications of graph neural network and how we can apply it in AEC? So like two straightforward application is like for generative room layout or optimizing a structural model or sizing it at the same time. And I think the best part which the graph neural network provides is the constraint information. So like in StyleGAN, you can create a latent space walk and generate different room sizes, but it can be very weird rooms. But that problem can be eliminated through constraint based approach, which the graph neural network have. What are like some like I think it's difficult to get everything at once because this is not a straightforward topic, but the intent was to like there might be like other areas or other channels or article which go into in depth about GNN, but the intent I had was like get an understanding of high level working of GNN and what are some applications and in AEC and focus more on AEC application part.
Yeah, thanks. Hi, Majid. Actually, I didn't kind of get a real guess of what you have explained, but because I am new to it, so uh, So, can you please suggest where to start for that? Because you have shared the very good resources.
Mhm.
So I just found out about the Deep Finder. So I also referred to that.
Mhm.
So
Yeah. So you
yeah,
mean detailed GNN or in general
I
a
you have explained a high level understanding
Hmm.
that I got a gist of it,
Mhm.
but how to appreciate it working? So like,
Yeah. So like if you watch these three videos, like they are like 20 to 30 minutes each, it will get
okay,
more deeper into like how to compute laws and like how like yeah. So sometimes because like I have watched like these videos, I might presume
Mhm.
that when I explain you might get it easily, but yeah. So this I think depending on the time you have, these resources will give you a good in-depth understanding.
Okay.
Yeah. And if you're
So you
just
have shared in GitHub, na? Okay, yeah, okay,
yeah, I can share it in the chat now as well. If you're just
yeah, yeah.
starting out, like I compiled a list of resources earlier where depending on the type, like the problem you are solving, you can
Yes, sure,
uh,
sure,
use these courses. Yeah, it's very beginner friendly where you start with exploration.
sure, sure. And I did search about the collab problem also, but I guess they were missing some dependency of Pi within, I guess, Torch within dependency. So I guess, so
Yeah,
sure. Sure.
yeah. Uh, I will look into
Yeah,
it
it's fine. Yeah,
yeah.
yeah,
It
that's
was
fine.
very unexpected actually. Last time I used it worked like sometimes it's either the version issue. Sorry,
Yeah,
Anik, I forgot to share the papers.
yeah, no, should I think it generally happens in Python. Well, it generally happens. So.
Okay, I'll share the
And what about like I have done some kind of other things as well. So if kind of GNN predicts something, so how can we identify false positive and false negative cases? I mean, it generally like there is some structure of how but real or fake. So
Mhm.
is there any manual intervention required? Like, because if yeah,
Yeah, so what you do generally is like in the original data set, you will
mm-hmm,
have images. Like it depends how you train. So if you just want to classify whether it's cat or dog or real or fake, you can have a
mm-hmm,
traditional model where in the data set you can say that for this examples it's fake. For this examples it's real. So once you train the data set, the model will learn that okay, if there are similar features or similar images, it's real, and it will predict that zero or one value or anything. So it depends how you have the training data and label the training data.
yeah, I mean it's more about validating the training data. Yeah, right.
Mhm.
But there are main kind of you never know how model arrive at that value because sometimes there are surprise kind of uh, yeah surprise prediction. So
Yeah, so that's why like it's important. Like it was similar case for me when I was working with GAN, and I used to live the training for epochs for a long time. But if you
mhm.
monitor the loss, it will give you some information that okay, is the model going in the right direction or wrong direction, and if the losses are
Okay.
decreasing, then it's predicting what it should predict, not the wrong stuff. Yeah,
Yeah, so thanks. Yes, thanks.
yeah, no problem.
Because I was kind of exploring about the interpretability of machine learning system. So there are tools that are given in Google Cloud platform as well. So uh, I just looked into it. So yeah, because most of these are kind of uh, something can be explained in something kind of it a black box. So
Yeah.
yeah. So,
Yeah, so it's a black box kind of thing, but once you uh, like in Deep Dream or other models, once you start inspecting the hidden layers of the network, you can get some insight which direction the model is being trained, where it's it going, but it's not straightforward. There are, yeah.
Yes, yes, I understand. Okay.
Thanks for asking. Yep.
Yeah, thanks.
Okay. Are there any other questions or things in general you want to discuss? That what are other ways? What are some problems in AEC which could be solved?
At this moment, I can't think of any problem, but do you have any suggestions of areas of research where this might be useful at?
Yeah. So let me share. So um, I think this is a good graph. When I was studying about it, that what are the different areas in AC and what are different models which people are using to solve that problem. So depending on the sector you're shortlisting, whether it's generative design or planning, safety, inspection, few like specific models would work better. So for example, in order to inspect whether the construction workers are wearing safety helmet on site, a convolutional neural network or computer vision like models would be more appropriate than a multi-perceptron model or graph network. So yeah, did I like get your question right? That you ask where GNN would be more applicable, right? Yeah. So
Yes.
I think for structures and like architecture, we saw a good solution of using graph for constraints and do generative solution of different room layouts or different sizing. So like most of the models I've seen is either generating more solutions or different solutions with similar on the design space, or faster calculation, like doing in the iteration which took 15 minutes, we can do it in very short period of time. So if the operation is very computationally heavy, you can use network to do faster computation. It can be also like daylight calculation or for MEP if there is a very big building and you need to do analysis. Uh,
Okay, thanks.
in yeah,
Um,
one sorry.
Please continue. I will talk after this.
Oh, yeah. I was just gonna say that there are also many variations of graph network, like graph convolutional neural network, graph transformer, graph attention, and those are also proving very good solution. So a traditional convolutional network versus graph convolutional network, there are some areas where GCN is better. So it's the magic or more efficiency happens when you combine different models to solve the problem. Because let's say if for a same safety problem you want to inspect whether there is a person, there is a head he's wearing, there is safety vest, you can define like through convolutional that okay, do object detection and do a bounding box. But if you can do the same with graph plus convolutional, where the graph can uh, identify constraint that there should be a head above a person's face and there should be a vest below and some relations between different variables, and then do convolutional. I think people are doing more research day by day. Sorry, Anik, you were saying something?
Yes, I'm very new to this whole AI ML thing. I'm just learning linear algebra and statistics and in those prerequisite part and also data structure algorithm. So thanks for showing us a path, that's all. And thanks for this initiative. Maybe you have a very good motives and it really gives me one motivation to do what is finding. And and your PPTs and slides, are you planning to share them to public or?
Yeah, I'll be sharing on the GitHub. So
Okay.
yeah,
Mhm.
let me share the GitHub link
Yeah,
on.
and the one you have sent it us with your meeting request, right?
Yeah, so this
Okay,
is the
so
main folder
yeah,
of,
yeah.
yeah, yeah. So I'll be sharing
Okay.
that.
Hmm.
And
And
honestly, like we all are on the same boat. Like I started few months back, so it's we are all
okay.
learning.
Okay, that's great. Good to know. Just one thing. So I was just wondering, while working with graph, so can we solve in general graph problems like traveling salesman problem and those things with GNN? So because
Yeah, like that's the first problem uh, that comes to mind using graph, because traveling salesman or transportation, those problems can be easily uh, modeled using graph. So that's why like it's those are solvable through GNN.
okay, okay, I got it. Okay, fine. So I will get back to more questions when I start exploring.
Yeah, for
Thanks
sure.
for this session. Thanks. Thanks for the initiative.
Yeah, thanks for joining and sharing your thoughts. So I was like, I'm thinking of doing this on a bi-weekly basis. So like there are three topics I had in mind for the next session, and I just wanted your your input. So we can do either like reinforcement learning overview in a deployment, or we can do some computer vision or a machine learning model deployment in browser. So what do you guys think would be a interesting topic? Uh,
For me, I personally think covering the prerequisite in one topic would be very helpful for us. Just that will help us to understand your next topics. That's what I personally think. I mean,
which one?
that's covering the prerequisites to understand all of this.
Oh, so like in this each like this are definitely like one session each. So in this session, like I'll start with like basics and prerequisite, and then we'll go deeper into theory. And like I think this was a good approach where we discuss theory first. We do one application in Colab, and then later one paper related to AC and discussion in the end. So yeah, it will go from basics, so don't worry about that.
Okay, thanks.
Yeah. So basically, like just to give you some idea, like if you have heard about AlphaGo, it's like those models developed by DeepMind use reinforcement learning, and which are solving some amazing problems. Computer vision, I think we see a lot of application in different areas of AEC, so it would be helpful to get an overview about how it works and what are various models. And model deployment, I think I just wanted that, okay, let's say you have existing trained model and you can do training on a cloud, or if you have heavy GPU you can do that. But if you don't have those resources, how can you use those model in browser and do some fun stuff with that? So that's what I wanted to cover in this.
On the third portion, ML model deployment, I have a question. Is it
Mhm.
possible to uh, read a TensorFlow model using Grasshopper or try to interface with one of those like a Dynamo or something like that? Because I know it's a little difficult because it uses Iron Python and it does not have Python 3. So I don't. Is there any other method that you could use or any other dependency that we can develop for that?
Yeah, that's a good question. So in one of the hackathon, what I did was from Grasshopper, I was requesting information for the input and output of the machine learning model. So like
Mhm.
it was a style transfer. So input image was in Grasshopper, then the information request was sent out of Grasshopper environment, and I was running Python code locally on my laptop through Flask server, and from
Okay.
that Flask server, it was computing the style transfer image, and then the output was sent again into Grasshopper environment. So that is one way if you want to use existing TensorFlow models.
Oh, okay.
Another way if you want to deploy Grasshopper machine learning locally. So most of these models are done in Python, but if you use C Sharp, you can deploy those models locally in a Grasshopper plugin. So I think Proving Ground has like Lunchbox ML, which is a machine learning plugin just for Grasshopper deployment. But the catch is that like most of the machine learning models you see are in Python, so you have limited like
Yes,
yeah.
that is true.
But I'm currently working on idea where I'm using like browser based training where
Okay.
I can train on the spot, like using the Magenta or something which Nono showed, and then I'm
Yeah.
connecting that input with Rhino compute in the browser, where let's
Okay.
say if I raise my hand, the building will get taller. If I raise wide my hand, it will get
Oh,
wide.
that's
So
pretty nice. That's pretty cool.
yeah, so I'm connecting both machine learning and Grasshopper in the browser. So let's see.
Okay. That'll be interesting to see how that figures out.
Mhm. So do you have any preference for the next topic?
I think you can do the reinforcement learning thing. I'm also pretty, that's among the basics. You can cover all the different types and then we maybe go on to deployment at a later session. So all the theory is covered. I'm okay with that idea. I'm completely uh, up for that
Yeah.
line of training.
Cool. Yeah, actually, I did recently a reinforcement learning in a hackathon where for AEC, like like for each project there are various resources in a company, like BIM engineers, executive, like various kind of engineers and higher level. So through reinforcement learning, we are doing a resource allocation problem where we have multiple projects and how different resources are allocated to different projects using reinforcement learning, and basically it rewards for maximum profit, shorter project duration. So we did that in the first week of Jan. So yeah, I think reinforcement learning, like many people say that it's the true AI where like it will find emergent patterns which the human has not seen before, and we can learn a lot from those. So it's a interesting topic to know at least general information, and when time comes you can based on your problem you can dig deeper, but it's good to have some basic knowledge. Cool. I think then
Yeah.
yeah, if you like, it looks like everyone is comfortable with the the structure. So this like each topic is for one session, so mostly like same time after 2 weeks, and I'll spend next few days to compile resources as I shared earlier. So if you have time, depending on like 30 minutes or 2 hours, you can study these topics. Cool. It was fun. I enjoyed it. It was good interaction. Any last moment things you want to share or comment?
Nothing. I was just going to thank you for allocating your time. And yes, this was a great session. I enjoyed it quite a bit. I think as like everyone, I'm also pretty new and I'm learning things as I go. And talking to people and interacting is one way that I'm getting to know more topics and getting exposed to the real applications within this industry. So thanks for organizing this. It was a great session.
Awesome. And I think like the most of my learning happened when I applied those models in a real life project. So maybe after 1 or 2 sessions, we can all do a similar hackathon type setting where we can all do a session, spend a couple of hours, and deploy a machine learning model for some problem. So hence we can brainstorm and think what are the ways we can solve a particular problem, and that will also give some confidence.
Yeah, that sounds like a good plan. Actually, I'm quite up for it.
Awesome. I think that's it for the night. Thank you guys for attending. See you soon. Bye.
Thank you. Have a great
Yeah,
day. Bye.
thanks. Yeah.